Hi, in this short presentation I will be talking about the Aurora Borealis, also known as Northern Lights. Aurora Borealis is a beautiful natural phenomenon that often occurs in the polar regions of Earth. It appears as colourful clouds and rays of green, red and blue light that streak across the sky. The aurora is formed when charged particles, electrons and protons, are guided by the Earth's magnetic field into the atmosphere around the north and south poles. When these particles collide with atoms and molecules of the upper atmosphere, some of the energy given off in these collisions are transformed into the visible light spectra that characterizes the aurora. The aurora has a variety of shapes, colors, and structures and can also change rapidly in time. During a typical night, the aurora often starts with a single long arc that stretches from horizon to horizon. Then curls or waves may start to form along the arc. It may also start to have vertical structures that look like thin, tall rays of light. This auroral activity can last anywhere from a few minutes to several hours. The Sun continuously emits protons and electrons, which are the byproducts of thermonuclear reactions occurring inside the Sun. As you can see from the equation, when two helium ions collide, protons are emitted. It's these protons and electrons, which are produced from ionization, that make up the solar wind, which travel away from the Sun through space at speeds of about 1,000,000 miles per hour. The steady solar wind is affected by Earth's magnetic field or magnetosphere. The solar wind flows around the magnetosphere much like a river flows around a stone. It also pushes on the magnetosphere and distorts it so that instead of a symmetric set of magnetic field lines, like one might have around a bar magnet, the magnetosphere is stretched and elongated into a comet shape with a long tail trailing away from Earth, as you can see from Figure 1. When there is a disturbance on the Sun, such like a solar flare, it can produce a disturbance in the solar wind. This in turn will cause a disturbance in the balance between the solar wind and the Earth's magnetic field, and as a result, electrons and protons are accelerated within the magnetosphere. The high-energy accelerated electrons and protons travelling down Earth's magnetic field lines collide with the upper atmosphere. The collisions can excite the atmospheric atom or molecule, or they can strip away its own electron and create an ion. The result is that the atmospheric atoms and molecules are excited to higher energy states. They emit energy in the form of light upon returning to their initial lower energy state. The particular colours we see in the auroral display depend on the specific gas struck by the energetic particles and the energy level to which it is excited. The two main atmospheric gases involved in the production of auroral lights are oxygen and nitrogen. Oxygen is responsible for the two primary colours, green, with a wavelength of roughly 560 nanometers, and a deep red one at roughly 630 nanometers. Nitrogen in an ionized state will produce a blue light, while neutral nitrogen creates purple colours. The process is similar to the lights that illuminate computer and TV screens. In the screen, a beam of electrons controlled by an electric and magnetic field strike the screen, making it glow in different colours, according to the type of chemical that coat the screen. Auroras stay above 95 kilometers of altitude, because at that altitude the atmosphere is so dense that they finally come to rest. Auroras form in an oval band centered at each magnetic pole. The width of the band ranges from 10 to 1,000 kilometers and approximately 3,000 kilometers from the magnetic poles. As auroral activity increases, the aurora not only increases in brightness, but also tends to move further towards the equator. These increases in activity are known as geomagnetic storms. Geomagnetic storms and the resulting auroral activity vary unpredictably throughout the year. This is because geomagnetic activity often results from events on the Sun. The following factors can increase your chance of seeing them. Time of day. Because the intensity of a light in an aurora is low, it can only be seen at night. Season. In the northern hemisphere, the best time to view an aurora is during the winter. At latitudes where auroras are most common, in the most polar regions, the weather tends to be clear during the middle of the night. Sun rotation. It takes the Sun 27 days to rotate one time around its axis, so 27 days after an auroral display, the active region on the Sun that caused the aurora will face Earth again. Although some solar activity in the region on the Sun might have decreased in the meantime, there is still a greater chance of auroral activity. Solar activity. Auroral activity also correlates with the activity of the Sun, which changes according to an 11-year solar cycle. In general, the more active the Sun, the greater the number of auroras. Also, weather can also affect your ability to view the aurora. Thanks for watching.